happy to introduce Mark to you. There's a connection to the previous speaker in that both have something to do with energy or come from the energy sector. But by glancing at the slide, you can also already see that Mark has used Data Science Retreat as an opportunity to actually do something else. You're all users of Google Maps. You're all users of Google Street View. You're all users of various technologies with your car. This is about something else that is maybe the most difficult thing if you're using a car in an urban space. And that is there's never, ever a free parking space when you need one. And this is what this is about. Please, Mark.
Thanks, Chris. So my presentation today is going to be about how I spent the last 6 weeks building my own version of a Google Street View car to map Berlin's parking regulations. So all of you with a driver's license, and probably those of you who don't have one, know this feeling. So some studies suggest that in the UK, for example, drivers spend on average around 4 days in a year just driving around looking for car parks. Another study suggests in some cities at particular times of the day, around a quarter of the vehicles on the road are just people driving around looking for car parks. So this is a huge problem. There's wasted fuel, wasted time, CO2 emissions. There's really nothing good about the situation. And one of the problems that drivers face is knowing where free spaces are. But another important problem is that they don't know where they're allowed to park. So they don't necessarily know where they should go to look for car parking. And they don't have an app to show them to do that either. Another driver that will need to know where to park quite soon is this one. So autonomous driving looks like it's quite close to coming to fruition, and these cars too will need to know where they're allowed to park when they drop their driver off at work or whatever. So the project objective that I decided on, an automated process for mapping a city's parking regulations. So as with any good data science project, I started with this question: which data am I going to use? And I came up with a few criteria for the data. The first is that it would need to enable the automated finding of parking signs. The second, the automated positioning of those signs. And thirdly, the ability to read the rules of the signs, if there are any rules associated with the sign. So the first step in my data seeking quest started, as most things do these days, with Google. So Google Street View is a treasure trove of images taken from the street. The API also returns the coordinates of the car when it took the image. So let's take a look. So this is Alte Schönhauser Straße in Berlin. You can see Berlin's beautiful Needle Tower in the background there. And if we take one step along the street, on the right we can see a parking sign, and it's looking quite promising. You know, the sign is clearly visible, the rules are legible, but if we take one more step, we find another sign, and for this case we see that the signs are not legible. And the problem with Google Street View is that sometimes it only takes an image, say, every 10 meters, so we might miss some signs, and if they're too far away, it can't actually resolve the text. Another big problem, particularly in Germany, is this privacy blurring, which exists in a lot of cases. So Google Street View is not a good candidate for this data. We may be able to position signs that we find, but we can't necessarily rely on it to find all the signs or to read the rules from the signs. So for my second iteration, I decided I would try and go out and collect my own data. This is the Garmin Verb Ultra 30. Comes complete with a high-definition video sensor, a GPS module, fisheye lens, and it also can be duct taped to the side of a car. So I went out and took some data with this, and the results speak for themselves. So the video sensor is not particularly good. The GPS sensor is also not a very good quality one. So in the end, it looks like we're taking a step backwards. You can't position the signs accurately, you can't read the rules, and it's questionable. It's not clear whether we can find the signs themselves. So at this stage, I decided I really needed to up my tech game. And in my mind, I had something perhaps in the like of this to take the images from the car. But after visiting my local camera rental shop, I ended up with something a little bit more modest. This is the Canon EOS Mark III. It's reasonably high grade camera. And I set it up in this way, looking out 45 degrees from the windscreen to capture signs on a good angle. But I still utilized the Garmin camera. I didn't neglect this. I had this set up looking orthogonally out the window for positioning, and I'll explain that a little bit later. I also had the good fortune to start at a job at a company recently which had a GPS sensor lying around, so I stuck that onto the roof as well. And you can see that the GPS, the quality of the GPS signal is much more accurate than previously. And the Canon camera is also able to resolve the signs. It takes very nice images. The exposure time is very short, so there's no blurring, and the sensor is very good quality. So with this last setup, we can position the signs, we can read the rules, but the question remains, can we use the video stream to actually automate the finding of the signs? And that was the next step of the project. So automatically finding signs, first step is to find candidates for signs. And if you look at this picture, the first thing you should notice is that the sign is basically a big red circle with some blue in the middle. So what I decided to do was to threshold the red image, threshold the blue, and then to get the edge, I dilated the blue pixels out so they overlap with the red, and then did pixel by pixel multiplication. And you end up with this quite nice circle for these signs. I then applied a so-called Howe transformation. Some of you may be familiar. It basically looks for the Howe circle transformation, looks for circles basically in an image like this. And hopefully you can see, yes, that it finds this particular sign quite nicely. And the next up is we have a very badly stitched together JPEGs into MovieScript so you can see the algorithm in action. This is from the Canon camera out of the windscreen, taking an image, and also the Garmin camera from orthogonally searching for signs, and eventually it'll find the sign here. So some of you with sharp eyes may have noticed that, particularly with the Garmin camera, there was a lot of rubbish being picked up. And the next step, of course, then is to try to discriminate that rubbish, discriminate the signs from the rubbish. So that's what I did next. And as a first step, I decided to do something simple, just to build some basic features. I asked how many red pixels are in the Howe circle. I asked how many blue pixels are in the Howe circle. I took some of the parameters from that the Howe transform spits out and put them into a basic logistic regression. And the performance for a data set that I made, about half signs, half rubbish, was reasonable at about 95% accuracy. I thought I would try a support vector machine to see if that improved things, and it didn't particularly. But as the last step, I recalled that we had a class in the data science retreat on transfer learning, which you guys have already heard a bit about today. So I decided to apply this method, which, as you know, is basically piggybacking off the hard work of some research lab somewhere. So I used VGG16 to generate features for my images, put those into a support vector machine, and ended up getting a great improvement. And this really just shows the how well these deep neural networks work for image classification. It's only binary classification, so it wasn't too difficult, but it was a great improvement. So pulling it all together. So on this map, you can see what's happening is that these red dots are where the car was when it spotted a sign from the Canon camera, and the blue dots when the Garmin camera spotted a sign. And I've gone back and forth a couple of times on these particular streets. So you can see there's still a little bit of work to do to position the signs. So what I decided to do as a simple first step is to say, when there's a cluster of signs from the Garmin camera, look for the sign when it's in the middle of the screen, because that's the point when the car is exactly going past the sign and it's the most accurate position. And you end up with something like this. So for example, this sign is signaling that this is the start of some parking regulation, this is the end of some parking regulation, and this sign with two arrows going both ways signifies that this is in the middle of some section. And zooming out to the map before, this is the signs that the algorithm found in this particular part of Mitte in Berlin. So there's some improvements that can be made, or quite a lot of improvements that can be made to this. One of the first is to identify these arrows, because it's quite important in determining in which direction the regulations apply, and therefore being able to draw these kind of parking pockets, so they call them. And I also spent a lot of time setting it up so that I could read this text. In the end, I didn't have time to work on that, but that would be an interesting next step, perhaps to use some text recognition algorithms to extract out the important information, like what time the parking regulations apply. A second important class of parking regulation is this, and I didn't work on this, but once the data science pipeline is set up, then including this in the flow shouldn't be too much more work. So that's the end of my presentation. Thanks for your attention. I hope you liked I hope you enjoyed.
Yes, please.
I have a command and a question. The command is about reading the text. Luckily, there is not too many different words on those blocks, so you might be able to learn just a couple of features.
Yeah.
Bemoner and
That's right.
like that, except numbers.
Yeah.
And the question is, I'm using a very manual park lot searching algorithm and also a manual parking algorithm in my brain. Should I be afraid that in the future a lot of my competitors have an automatic system to spot the spots, so that I will disimprove my very, let's say, above average searching time?
Possibly, but everyone is at risk of this from machine learning, I think.
Oh God, I gotta get we call it, okay, thanks.
Yes, please.
Yeah. So great work. I think it's like really nice to use for parking inspectors actually. But if I'm a company that wants to find out which places people park in, I can just look at which places have cars throughout various hours of the day and use that as my signal rather than the parking regulation. Right?
Yes, you could. And where would you get the data for that?
Google Street Map.
Yes, you could. Yeah, so that would be an alternative method that you could take what's actually happening on the ground and say at this particular time of day there are cars here, so assume you're going to park here. That could be another approach you could take. Yeah.
And you can come and automate this traffic inspectors.
Yeah, I suppose. Yeah.
But the Google Street Maps, it's only taking pictures every now and then, weeks. Or
Yeah,
months.
that's right.
But you can recognize the car. It's like a big thing.
Yeah.
But you don't see the ticket.
And you would need a kind of every hour, every half hour.
Yeah. And you can see from where people park, then you can see that some hours people park there less, or maybe it's illegal.
I did consider using satellite imagery for that. But the problem with satellite imagery is that what's the word for it? It comes over the same time every day, so you can't get this time sequence that you would want for that.
I suppose the next thing you're going to do is have a drone.
Yeah, well, I did. Yeah.
Okay, next question, please. Any more? Okay, then thank you, Mark.
Thanks.